Time for a pop quiz. Hardly even a practice test.
Nicely done, Turdy.
Come on, Jeffrey, you can do it. Pay
Hi, Jeff.
Put your back
Welcome in.
into it. Tell us why. Show us how. Look at where you came from. Look at you now.
I know, it feels kind of like a marathon today. We got stream number 3 starting up pretty soon here. Which reminds me, I need to shut off that. So entrance songs, a lot of the ones that we've done so far have come from, well, they've kind of evolved to include these new AI generated songs. So if you make a really fun suggestion for an AI gen song, we can probably turn something into an entrance song. But it also takes me like a full day usually to like edit everything. So it might not happen till this like spring when I get more time. All right, we're live over on Twitch, just so you know, Cluster. But there's no rush. We got a few more minutes yet. I'll just be bantering with chat a little bit.
Oh yes, sure. In fact, I'm reading chat too.
Oh, one of the darn frickin' Discord. Okay, let's see if I can figure this out, chat. Okay, there we go.
And Sancho, what are you trying to figure out?
Oh, sometimes Discord goes through the wrong, like, electronic channel or something, and then, so it kind of pushes your voice back into my speakers, even though I haven't told the electronics to do it. It's really, really weird.
Right, I see.
Oh, Jeff is asking about your accent. I don't know if it's British, is it?
I suppose, like, part of it is. It's a weird thing that is happening with me. Yes, it is.
There you go. Yeah, welcome on in, Turdy. Welcome in, Jeff. Welcome in. Oh, hi, Dexy. How are you doing? And Samoyo. First message. What if Penn was at the center? I don't know. The world would implode.
I'm looking at you on the stream, and you are not in the center. You're slightly to the right.
Oh, gosh. I'm not living up to my name. Oh no.
You got to change that stream layout.
All right, now we're gonna pop
Meanwhile,
over. Let's pop over here. That's not the right one. That's the right one.
Damn, I didn't know my presentation was a black screen.
Oh, Discord! I'm gonna punch Discord if he keeps doing this on me.
Take your time with it. We got like 2 minutes until we start. Even then, there's a pretty likely chance that I might actually run over time because I have to cover a whole entire chapter. So that kind of sucks. Also, I'm very sorry for bringing everyone up at whatever time it is where you are residing. But yeah, this is what it is. Welcome to British Texas.
Hey, I mean...
Yes, that's the joke. Sorry?
I was gonna say thank you very much for like agreeing to present at this time. I know there's actually people that I think appreciate a little bit of a later start Pacific time because they can actually attend some of these presentations, so...
My guess is that some people would be at work and, you know, while they're at work, they can't, you know, whip open their phone and look at Twitch while working. That's like texting and driving, except the risk is you'll get caught by your supervisors or higher ups. Both of
Right.
them are not recommended, guys. Don't text and drive.
Oh, it's 8 a.m. where you are, Turdy. That's Pakistan, right? What is that? For all y there exists an x, pen x, and center. Oh my gosh. 8 p.m. where you are, Jeff? So you're right beside me. In Delaware, Colorado. Okay, I was wondering. Alrighty, well, we got
Right,
8
1 minute
viewers
till,
out
so-
over in Twitch, and then we got a couple that popped in over here in the Discord, so welcome Cart, welcome PM. I am monitoring the chat, and I know Cluster will be doing that as well, so you're welcome to use the chat interface here in lectures if you have any questions along the way. Otherwise, I'm going to go ahead and say welcome on in. This is presentation number, what is this, number 7? Number 8? Where are we? Is number...
it 7? I'm pretty sure it's 7.
I think it's 7, yeah. Presentation number 7. So Cluster's here to chat a little bit. Well, welcome back, first of all, and here to chat a little bit about elementary matrices and kind of how we think about their use with regards to systems of linear equations.
Yes,
Jeff
thank you
is
very
asking
much.
a very important question, Cluster. Very important.
Does Cluster have a streamer username? Yes, it's called Cluster, and it also doesn't exist on YouTube or Twitch, not yet anyway. But I am streaming on Discord, so yes, that is my streamer username if you're wondering. Yes, so with that, here comes presentation number 7, and I'm back. Sorry, not sorry. If you didn't miss me, too bad. Right, today we're discussing a very important topic called systems of linear equations and how to use row and possibly column operations to basically solve them. Before we actually get into them though, let's actually have a review, a summary of what happened last lecture. So first we had our change of basis matrix. Now, this shit kind of made me really confused when I first studied them, but this book kind of cleared things up. The change of basis matrix is just a special identity matrix which goes from one basis to another in the same vector space. Amazing. Now, basically, the change of basis matrix is meant to take in a coordinate vector, not an actual vector, right? Because we're talking about bases here and not different spaces. Basically, if you want to if t is like a linear operator as usual, you can represent it in terms of some basis as its change of basis matrix, and all you have to do is just if you want to change the transformation t so that it acts in a different basis called gamma here, then what you can basically do is just surround it with a change of basis matrix and its inverse. So yes, you can do that. All right, what next? Furthermore, what happens here, you can basically represent any coordinate vector of a basis matrix in another basis by just applying the one of the standard basis vectors. That's great. Hang on, something is wrong here. I need to be able to... There it is. Okay. Technical difficulties, guys, but we're getting through this just fine. All right, so that's the change of basis matrix. Now we have dual spaces, which are possibly even more confusing, but I kind of realize what's going on after reading Friedberg. So the dual space is pretty much a mapping where you go from a vector space to just the field of scalars. That's all that happens. And of course, the field of scalars can be seen as a vector space, if I'm not wrong. And as usual, you can basically decompose your field here into this little summation here, kind of like when you have linear combinations of vectors, except instead of the vectors themselves, you literally plug them into your linear functional and multiply by one of your basis functionals. How about that? Yes. And we also introduced the transpose in that chapter as well, which pretty much kind of switches the space around and also does kind of weird things in the linear transformation space. And if you apply T transpose like this to a linear functional, you kind of just switch it around. And when you try and represent it as a change of basis matrix or like some sort of matrix with respect to two vector spaces, there's your little identity there. I think some people out here would have a much better explanation, a much better piece of intuition on how this works. Personally, I'm still not 100% like cool with it yet. Because like I said before, this kind of stuff is things that really confused me when I first studied it. Now, and even more confusingly, we're not done yet, there's the double dual space, which I've never seen before, but apparently it's isomorphic with the original space here. So that's a thing. Maybe you guys can also describe it better than I can. Right, today's topics, there they are. Very easy, 3.1 to 3.4. If you read the book, then you can fall asleep now. Otherwise, what's going to happen is the first chapter, or well, section, is going to go over what elementary matrix operations are, okay, how they can be represented as matrices themselves. Then after that, here comes the two sections which don't seem very imposing, but they actually are, and they also seem to not have much use, and you're probably also right, but they're also important for developing the theory for when you actually solve a linear system in the most efficient way possible. Yes. So that's how you'd consider rank when it comes to matrices and performing systems of linear equation solving. Now, why? Well, if you find rank preserving operations on matrices, you can basically find the rank of its associated linear transformation. And you can also determine the number of linearly independent rows and columns in a matrix/linear transformation. Keep that in mind. You're going to see why that's very important. And of course, we have our original goal to determine the solutions to a linear system. Right, let's get on with it. 3.1. So, first of all, what's an elementary row and column operation? Well, here they are. So you guys, I introduced this in the second lecture, but you know, it's been 5 lectures since then. So let's actually go ahead and refresh our memories on that. So we're going to call a type 1 type 1 operation as when you swap two columns or rows of a matrix. So the row version will be denoted as 1R, the column version will be denoted as 1C. Similar action when it comes to multiplying any row or column of A by a non-zero scalar. That's a type 2 operation. On the row, it's R, column C. And lastly, when you add a scalar multiple to a different column, type 3R, type 3C. Is there a type 3 diabetes? You guys can answer that in chat. I don't know. Nevertheless, let's actually see some examples of this stuff. So let's say you have this matrix here. It's a classic 3x4 matrix. Now, we represent switching two columns or rows. So in this case, we're switching two rows here with the double-sided arrow. So R1 means row 1, R2 means row 2. Now, when you switch row 1 and row 2, this row here goes up top, and this row here switches its place, which kind of looks like the circle of life, but a lot more crude. Nevertheless, that's a 1R operation. C1 plus C3, that's literally saying grab C1 and set it to C1 plus C3. So here is C1 here is C3. If you're a programmer, no zero indexing, sorry, not sorry. So over here, we'd grab C1, and then for each element in C1, we'd go ahead and add each element of C3. So this is plus 3 here, this is minus 1, and this is plus 1. And your new matrix will be just 4, 1, 5, and then so on and so forth. Everything else stays the same. All right, that's a column operation. And lastly, if we go on to the next slide, here is our type 3 operation. Whoop. There it is, where you can basically grab the second row here and subtract 3 of the first row. I'm great at drawing, by the way. So here's row 2. In this case, you'd grab this 2 here, minus 3 times 1. This one here, you'd go minus 3 times 2, and so on and so forth. You get the idea. That's your 3R operation. You can kind of figure out how the respective operations for each type, whether it's a column or row. The ones I didn't show here, you can kind of figure out how they work. That's an exercise, by the way. Okay, here's a definition. Basically, this is the point where we kind of try and bridge the gap between the theoretical operations, which we just introduced back here, and relate them to how they would be as matrices. So a matrix, which is square, by the way, is elementary if it performs the corresponding elementary operation on the identity matrix. Now, we use the identity matrix here because basically the identity matrix kind of does nothing, right? So if you apply the identity matrix to any other matrix via matrix multiplication, nothing happens. So if you grab your elementary matrix here, this will just kind of be your elementary matrix. So a bit confusing, kind of, but think of it just, oh, it's an elementary matrix that does an elementary operation on some other matrix. The identity one's just the easiest one to choose, I guess. Okay, now, well, what's going on here? Can I please go to the next slide? Thank you. Okay, so here's an example of an elementary matrix. If you left to multiply this matrix on some other matrix, let's say this very creative one, A, B, C, D, E, F, G, H, I, like this. I is not the imaginary number. This will actually swap rows 1 and 2. I will leave it up to you guys to try and verify this yourself. But actually, do we have time for that? I'll just do it in here anyway. So what I would imagine is for this first entry here, I'd grab A, D, and G. So this would be D here. Where's my eraser? There it is. This would be D here. What else? This would be A here, and this would be G down the bottom. So you can kind of see by just doing the first column, you can kind of imply that this thing is kind of switching the first and second rows here, which is doing a type 1R operation. See, D is here, A is now here, kind of did a switcheroo here. It's going to do the same thing to the other columns, as you will see if you try it yourself. Now, here's a bit of a question for you guys. We'll just be really quick about this one. I'll just read from chat. What would happen if you do a right multiplication? Like I wrote, it's a type 1C operation to give you a hint, but what is it exactly going to do? I'm gonna have to check Discord too. So Brian, of course, knows what he's doing, so I'm not gonna actually listen to what he said in Discord. No, it's not gonna switch rows, da turtle. It says type 1C, so that means it's probably gonna do something to the columns, right? We had this on the previous slide. But yeah, there for now. Basically, this will switch columns 1 and 2 of the original matrix. So let's actually give it a try, since I think we need a bit more familiarity here. So 0, 1, 0, 1, 0, 0, 0, 0, 1. If you right multiply here, what happens? So might be in a lack of space here, but let's take a look at this column here. If I multiply with each corresponding row, the first column will be B, E, and F. And you can already see, look, B, E, and H here were once on the second column, C2, but now they're on C1. And look at what happens when I go ahead and do the second column here. This will give us A, D, and G. And the last column will basically stay the same. See, look at that. We switched both the first and the second columns by a right multiplication of the exact same matrix. Amazing, isn't it? Okay, now here's another example of an elementary matrix. This time we have a 4 in the bottom. Now, if you left multiply this matrix, what's going to happen is the third row is going to be 4 times itself. Let's actually give it a try very quickly. So these two are just going to stay the same, A, B, C, D, E, F, and then have a look at the last row here. This G is going to be multiplied by the 4 here, so we get 4G, and so on, 4H, 4I. And since I think we need to actually move a bit faster here, so I'm going to actually give this one away and say, if you do a right multiplication, you're going to basically multiply the third column by 4. So instead of multiplying the the third row down the bottom here by 4, you're going to be doing it to the third column if you do a right multiplication. Very nice. Okay, and lastly, this one's going to look the most confusing, but if you actually give this a bit of practice, it'll get easier. This matrix is going to multiply the third row by -2, and it will add the result to the second row. So if you kind of think about, you can think about it like this. If you do a left multiplication with whatever's in here, the result of the second row is going to correspond. Is my program lagging? No, it's not. Good. The second row is going to correspond to anything that happens on this row here. So you can kind of see, it looks like we're grabbing 1 times the second row, and this looks like -2 times the third row because of the corresponding column it's at. But yes, and a right multiplication, oh, this is going to be a bit difficult, but if you actually just put the third column for what it is here, it looks like, oh, um, it looks like we're going to grab the third column as usual, and we're going to do -2 times the second column, if I'm not wrong. Is that right? Yeah, I think that is. Brian, can you confirm this for me? Yeah, I think this elementary matrix here, if you do a right multiplication, what's going to happen is the third column is going to be added with added by -2 times the second column. That's what my belief is. Yeah, yeah, yeah. Yeah, very nice. Okay, now here's where we kind of join the last two bits together with the matrices and the theoretical operations. Here's our theorem. Let's say you can obtain some other matrix B from, you can obtain some other matrix B here by performing an elementary operation on A, um, which was one of the type 1R, 1, 2R, 3R, etc. Then there's a corresponding elementary matrix that kind of does the same thing for you. Um, if it's a column operation, it's going to be like this thing here. Sorry, that's a column operation where you do a right multiplication, and then this one here is where you do your row operation. Um, now the proof of this is actually very involved. So what's going to happen is, oh, I'm just going to leave this as an exercise for you guys. There's the hint I'm going to give is that you do an induction on M and N. I think this is also given in the book, so you should be in good hands as well on that front. So now that we know that you can get another matrix from an original one using an elementary operation, now we're going to actually talk about whether these elementary matrices are actually invertible. And in the luckily for us, yes, they are invertible, and the inverse has the same type. To see how, let's say E is elementary. So from the previous theorem, if we set B equals I, sorry, my cursor's disappeared for some reason. So if we have B equals I here, so from the previous theorem, you could obtain B from A using an elementary operation. So let's say you can obtain from E by reversing the operation entailed by E. This is pretty much just logically the inverse of the elementary matrix. So if you just simply reverse the operation entailed by the matrix, this is also just an elementary matrix. So for example, if you multiply row 1 by 3, then all you just do is just divide row 1 by 3, which is the same as multiplying row 1 by a factor of 1/3. So that's the inverse of that operation, which therefore has a corresponding inverse matrix. If you do a type 3R operation where you like multiply 2 times the third row and then add it to the second row, you just reverse the operation by subtracting 2 times the third row from the second row. So, sorry, let me just get this thing sorted where my cursor has disappeared. I don't know why it's done that. Uh, Sorry, I've never had this happen to me before. It's very hard to deal with. I can't see where I'm drawing. It looks like I have to deal with this then. One day I'll figure it out. This is the first time it's happened to me. Nevertheless, so that's basically the end of this little section here. We'll do a quick quiz and then we'll get to the next one. So question 1, an elementary matrix is always square. Can we get a poll on Yep. How long did you set the poll for? Yeah, maybe 30 seconds will do. My cursor has reappeared. I don't know, it just loves doing that. Yep, that is true. I did mention that in one of the previous definitions, so I guess this was a pretty easy one to make you guys feel a bit better. All right, number 2. The identity matrix is an elementary matrix. Now let's start thinking a bit here. Is the identity matrix an elementary matrix? That's okay. We'll just stop the poll at about 30 seconds then. Yeah. It's a very, very arguable answer. Yeah, so I think that's about 30 seconds. We'll leave it there. I'm gonna actually say it's true because if you think about it, what's actually happening in the elementary matrix? I would claim that this is a 2R operation. This is a 2R operation or a 2C operation. I'll call it a 2R for now so that it's a bit easier for us to see. If you just focus on this one here, then all it's saying is you're multiplying the second row by 1, right? Which pretty much does nothing, but it's still, technically speaking, a 2R operation. So that's why I've gone ahead and said it's true. Some people will say, no, it's not an elementary matrix. But I will say yes, because it is what it is. It's also invertible, by the way. If you want to undo a 1 times multiplication, you just divide by 1. Yeah, how about that? Which is just the identity matrix once again. All right, the product of 2 elementary matrix is always an elementary matrix. Here we go. Now things are starting to get a bit tough. Or are they? Fami,
Yeah, go ahead. Cluster.
yeah, Fami, we're using Friedberg linear algebra. Funnily enough, this is the first time I've seen this book, but I suppose we're not actually getting any answers in the poll, but that's okay. I can just reveal it right here. No, it's not, because what you can essentially do is if you do basically C1, minus C3, and then you go ahead and do R3 to R3 minus 1 here. If you get the matrix representations of these two operations and then multiply them together, you're pretty much doing these things back to back. So let's say this is 1 here, and then this is 2. When you multiply these things together, you're doing them back to back, and the consequent matrix here is essentially doing two different operations, while elementary operations themselves and elementary matrices should only do one operation. So it can only do a single 1R operation, right? For example, or it can only do a single 1C or a 2R or a 2C, etc. But you cannot put them together in the same matrix. It's no longer elementary if you do that. Okay, now that we got that out of the way, let's do the last one real quick. The inverse of an elementary matrix is always elementary.
Pop that
Okay,
poll up there.
vote now on your phones.
Phone a friend.
Yep. Vote now on your phones. Yes. Don't drop your phone. You'll need it. I think. Maybe.
I hate when I'm like looking at my phone in bed and it falls on my face.
Oh, yeah. I don't look at my phone while I'm in bed, but yeah, I can totally understand that.
All right, we got one vote in for true.
Okay. Yes, and luckily for you, whoever that voter was, you're right. Well done. Yes. And I've kind of made that point clear a few times, but yes, all the more merit to you. Let's do this one really quick. I think we're still on time because there's 4 sections. The transpose of an elementary matrix is always elementary. Let's see what answers we get for that.
Oh, welcome in, Joe. Just woke up? Cool. So we got a poll for you. Here's our question. I'm just going to pop
We're on
that poll
Q5
up.
now.
Boom, Q5. So do you think the transpose of an elementary matrix is always elementary? True or false?
For those who just joined in, an elementary matrix pretty much does, it either switches rows, switches columns, or it multiplies a row or column by a scalar multiple, or you can add a row or column by a corresponding scalar multiple of another row or column. Okay, that's about 30 seconds, and 1 vote for true, which is correct. And the reason that is because if you actually have a look back up here, let's have a look. What happens if you take the transpose of this matrix? Well, these 2 elements switch. These are all zeros, so nothing happens. These are zeros, nothing happens. So basically you get the same matrix back, etc., etc. So if you switch 2 rows, doing the transpose kind of does the same thing. If you take the transpose of a 2R operation or 2C operation, like again, this is a diagonal matrix, taking the transpose does absolutely nothing. So it's still a 2R, 2C operation. And lastly, if you take the transpose of this matrix, this 2 just happens to go down here, which just means it will go ahead and, if it's a type 3R operation, all it will do is just add -2 times the second row to the third row, which is still an elementary operation. So I guess this case was a bit of harder to distinguish, but very well done. Okay, now next section, where we actually talk about how the rank of a matrix relates to a linear system of equations, or elementary matrices, pretty much. All right, so first of all, we actually haven't defined what the rank of a matrix is. We know what the rank of a linear transformation is, but not a matrix. So let's actually go ahead and clear that up. So the rank of a matrix is basically the rank of its corresponding linear transformation, like this. Where LA is just a transformation from f of n to f of n. And all it really is if you apply L of A to a vector, then that's the same as multiplying that vector by A on the left, of course. There it is. Very nice. And to remind you guys as well, the rank of a linear transformation is just the dimension of its range. So we're going to see that quite a bit. Now, here's a little theorem for us. If you actually go ahead and take any linear transformation T, and you actually turn it into a matrix with respect to 2 bases, then their rank is the same. Where this rank is basically the dimension of your range as before, and this one is the rank of a matrix, yes, as per our definition here. And the proof of this is for you guys. It's an exercise in the book. So I think you're going to actually give that one a try yourselves when it gets included in the exercises section. So here we go. So let's actually have a look at some properties of the matrix rank. The intuition is that it might be hard to find the rank of a regular transformation, but I can definitely say for sure that it's going to be easier to find the rank of a matrix. You might not agree with me now because we haven't seen much, but let's actually see why that's the case. And it's to do with applying rank preserving operations. So here's our theorem here. And basically, if you have matrix A and you have P and Q as invertible matrices, then what you can essentially do is you can right multiply by Q, and the corresponding rank is still the same, by the way, which is pretty curious. If you left multiply by P, and by the way, I'll say it again, P and Q are invertible. So maybe that will have to kind of do with, like all these rank preserving things will have to do with that. And consequently, if you multiply left and right by invertible matrices, then the rank of the matrix is still unchanged. Amazing. Now, to actually see why the first one works, essentially, you can write the linear transformation corresponding with the matrix AQ as just the composition of the two. And the range, well, to essentially get every single element in the range, all you just do is just grab every single vector in the input space and just plug everything in, and that's pretty much the range. Everything that you can possibly get. And since Q is invertible, this is pretty much just the same as applying f of n. So if to be a bit more specific here, L of Q, because Q is invertible, L of Q is a bijection, or a one-to-one correspondence. So that means if I have f of n here, then it just maps like some, like if you grab an element here, it might map to like somewhere up here. But for every element back here in the range, there's always an input element to associate it with, and it's unique, which is why you can basically just write L of A of f of n here, which is just the range of L of A. Now, consequently, if you go ahead and do your rank on A of Q, then it's pretty obvious from here that since the ranges are the same, you just get rank of A back. Now, for the second one, we're actually going to leave this as an exercise where we will get you guys to draw from a previous section. And the idea is that you're just multiplying the left, like on the left, by an invertible matrix, which means you're kind of going to use a very similar approach to what you did to do part one here, which is why we can basically leave it as an exercise. Of course, once this lecture is over, you guys have any questions and you're like really stuck after trying it, please go ahead and ask us. To show part three, you just go ahead and use the previous two parts to your advantage. And the idea that matrices, when you multiply them together, are associative. So basically, we're treating PAQ here as a right multiplication of Q, which means the rank does not change, and by 2, you just get rank of A back. Pretty simple stuff. Okay, there are consequences for being able to preserve the rank of a matrix like this. Elementary row and column operations are rank preserving. This is pretty obvious. Why? because each elementary matrix we introduced earlier is invertible. So you can just literally apply the previous theorem and you're all good. I don't think we really need to go through this proof. I literally explained the intuition behind it. So yeah, if you want, go ahead and read this afterwards. But we did this rigorously for row operations. The proof for column operations, of course, is left as an exercise. Remember, this section here is going to be long and painful. So I'm going to have to skip over a few things. Also, in the book, they did say you should, do those things as an exercise. Okay, so now, we now know about how to preserve the rank of a matrix regardless of how complex it is. You just multiply it by invertible matrices. Now let's go ahead and figure out how to determine the rank of a matrix. Let's actually see how it works. So if you do your invertible matrix multiplication, you'll eventually realize that the rank of matrix A is basically the span of the columns of the matrix, which actually might not seem very intuitive, but let's actually look into this a bit. So first of all, you have your matrix and its association with its linear transform, and you have its standard basis here, which of course will span f of n. And if you think about it, to get each column of the matrix A, you just multiply by the corresponding basis vector, standard basis vector. What happens? The range will pretty much just be here, span of the columns, pretty simple stuff here. And consequently, by just the rank is basically going to be the dimension of the span. There it is. That's a typo. Thank God I caught that. So that's the end of the proof. Brilliant. So before I move on, I know I kind of glossed over this proof a bit. I'm just going to check if anyone asked any questions about this. No, it seems not. So I'll leave it for a bit later. So let's actually give an example of this. So here's our matrix here by performing, so the first step here. So if you perform these column operations in order, or row operations, so basically row 2 set to row 2 minus row 1, row 3 set to row 3 minus row 1, and etc. What essentially ends up happening is we end up being left with this matrix. Now, I'm going to say it again. If you perform these row operations, I'm just going to call these E1 and E2. They're associated with matrices, remember? So, and down here, I'll call this G1 and G2. So to arrive at this matrix, what's essentially happened is I've gone ahead and done E1 here, and then E2, and then G1, and then G2, like this. And remember, these elementary matrices are invertible, which means the corresponding rank of this matrix is still going to be the same as rank of A, like this. Which is why, when we determine the rank of this matrix, we also determine the rank of A here. So, and we know the previous theorem said that it's the dimension of the span of the columns. So, as you can see, these two vectors are linearly dependent, which means one of them is redundant. I'm going to go ahead and exclude this one here. So now, the dimension of the span of the columns has to be 2, because obviously these two columns are linearly independent, right? And I've excluded the offending column, right? There it is. The dimension of the span of the columns is clearly 2. Beautiful. All right. Now, we're going to introduce a matrix transformation theorem here. basically, if you have a matrix A and it has a rank R, then you can basically transform it into this little diagonal matrix here, where the first the first R rows, sorry, the first R elements of the diagonal are just 1, like this. So if you have a rank of 3, so R of 3 here, then this part here will be your I of R, so I of 3 in this case, and then the rest of everything is just 0. That's the idea. And the reason you can do it is because you can use finitely many row and column operations, basically. And I've explained this just now. O1, O2, and O3 are just 0 matrices. So to give you an example of this, here is a really large matrix, which I will not have time to do all the transformations myself. So I will get you guys to do this in your own time. You can transform this into I of 3 at the top. This is O of 1. This is O of 2, and this is O of 3. Very nice. So if you just go ahead and use finitely many row and column operations to basically get ones in these positions and then end up with 0 everywhere else, which is possible, by the way, then you pretty much have the rank of the matrix. And the real proof is by induction on M and N. It's extremely involved. I actually had the proof in here originally, but I realized it's too long-winded, and I think a lot of you guys would actually get lost on it. I know I would if I were a regular viewer, so don't feel too bad about that. So the sketch pretty much says you can write A like this. So all I've gone ahead and done is I just have the first row and the first column here, because this is by induction, quotation marks, and the rest of the matrix I'll just go ahead and creatively call it A prime here. All right, so the first thing I'm going to do is I'm going to do a 2R operation. I'm going to divide the first row by A of 1, 1, like this. Oh, but cluster, what happens if A of 1, 1 is 0? Then you'll be dividing by 0. And I'll say, yes, that's true. In that case, just use an appropriate column or row operation to pretty much go ahead and find a non-zero row and just shift it up here like this. How about that? Maybe A21 is 0 as well. That's fine. Pick a different row, goddammit, or pick a different column. You get the idea. So we've gone ahead and done a 2R operation to get a 1 in the top left-hand corner. Okay, what happens next? I'm going to go ahead and do a bunch of 3C operations here. I'm going to use this one here and subtract scalar multiples of, you know, whatever this was, A12 divided by A11. So I'm going to subtract by A12 divide A11 of the first column, and then so on, to basically get zeros all the way up here. Beautiful. And the consequence of doing this is that since these elements here may not necessarily be 0, they're also going to transform the elements in A prime. So we're going to call it B prime for now. But that shouldn't matter too much. Because the main point is, all I want to do is get a 1 in the top left-hand corner, and then make everything to the right of it 0 and everything below it 0. And from here, transforming A21 and all the way down to AM1 to 0 is pretty easy. Just go ahead and do a bunch of 3R operations. Beautiful. Now, what happens next? That's our first step done. Inductive step, okay. What's going to happen? You can just do the same thing on B prime, right? Basically, B prime is in this set of matrices which have 1 less column and 1 less row, and the rank is the same as A, the original matrix, but just subtract 1. This is an exercise for you to try, because verifying it here, too long-winded as usual. And as I said earlier, repeat the process inductively to obtain the desired form. So there you have it. That's the proof sketch. Okay, so what are the consequences? Well, basically, if you start off with the matrix A, then there are invertible matrices B and C, such that you can transform it into the previous form we had earlier, where you had the identity matrix with rank R. And why is that? Very simple. When you go ahead and basically multiply by elementary row and column operations, so E1, E2, E3 like this. These are row operations, by the way. If you go ahead and do this, excuse me, can you please write? Thank you. Okay. If you go ahead and do a bunch of elementary row operations, then it turns out that if you multiply a bunch of invertible matrices together, finitely many by the way, then the resulting matrix is also invertible. Same thing if you do your column operations. Like this. This is also invertible. Which is why this corollary works. And at this point, I don't even have to explain the proof to you because it literally has the same idea. There you have it. Okay, what's the other consequence? Well, the rank of a transpose of a matrix is the same as the rank of A. Why is that? Pretty simple. Let's say you have I of R, O of 1, O of 2, O of 3 here. If you take the transpose of this little bugger, what happens? Well, I of R stays where it is because it's the transpose. This is a 2 down the bottom. O of 2 goes up here, O of 1 goes up here, and I think O of 3 goes down here as well. And if I'm not wrong, I think you have to take the transpose of these matrices too. But the result is clear. This is still a zero matrix, that's still a zero matrix, that's still a zero matrix, and this is still I of R. So that's why the rank is still the same. And the rank of A is still the span of its rows. Pretty obvious stuff. You guys can read the proof. I'm a bit worried that we're going to be low on time by the time we finish this section. But yeah, please stop me if I'm going too quickly. So there you have it. There it is. All right. Every invertible matrix is also a product of elementary matrices. And, well, that's kind of interesting. I thought we kind of said that earlier, but the difference between this corollary and what I said earlier is that now it generalizes to every invertible matrix. And I'll leave you guys to actually go, no, not leave you guys, but basically if A is invertible, then the rank is n, of course, because if you actually do your matrix transformation theorem, basically what's going to happen is you have your standard matrix form here, which is what you'll end up reducing to, but these zero matrices are basically non-existent, which means this I of R is actually I of n, which means your rank of A is n. That's why. So by row and column operations, this D here, which is your reduced matrix, is the identity matrix, and you can write D as B times A times C, where B and C are your invertible matrices composed of elementary matrices. So by matrix algebra, D is just the identity matrix, as we saw earlier, and suddenly you can just write A as the product of two elementary matrices, or rather, two invertible matrices. And you're done. How cool is that? Okay, now we know how to determine the rank of a matrix. you just go ahead and perform a million column operations and a million row operations to get this form here. I'm going to sound like a broken record, but I don't want to lose you guys here. Anything can happen. I know I can get lost too. So that's how you compute the rank of a matrix. Get it into this form at the very most. Now, from here, you can test to determine whether a matrix is invertible. Oh my God, you can do that? Interesting. But to actually get to getting the inverse of a matrix, let's actually introduce the augmented matrix first. And it's literally just a concatenation of two matrices into the same matrix. It's like gluing things together with super glue. But in this case, you can kind of easily take them apart if you wanted to. So it's a column-based concatenation. So if I were to go ahead and I think we have an example on the next slide. No, we don't. But imagine you have 0, 1, 1 like this. This is one matrix here. Well, this will be A here, and then B will kind of be like one. Don't do that. Cooperate with me. 9, 10, 11, 12. So here we have an example of two matrices that have been glued together, and this little bar here is our glue. So that's what your little augmented matrix can look like. So from here, let's say the matrix A is invertible. Let's suppose it's the case. Now I'm going to go ahead and form this matrix here, augmented, where the right-hand side is just the identity matrix, left-hand side is A. Now, what happens next? By exercise 15, what essentially happens is if you multiply an augmented matrix, or pretty much any matrix that has been dissected into blocks, then you'll essentially be multiplying the same matrix on the left-hand side by both parts. And consequently, A inverse of A is just the inverse, and A inverse of identity is just A inverse. Okay, so that's the plan. Multiply by the inverse, and then the right-hand side becomes the inverse. Oh, but hang on. A inverse is invertible. So why don't we use elementary row operations to go ahead and do that, right? So the logic here is if you transform this augmented matrix using just finitely many row operations so that the left-hand side becomes the identity matrix, then it should be the case that the right-hand side should just be A inverse. I hope that makes sense, given what we've just seen earlier. And that's our process of inverting a matrix. How about that? So let's actually give this a try to see if this works. So let's say we want to get the inverse of this matrix. So I construct the augmented matrix below. So in this case, I go ahead and do this. This is no longer A. This is a bar. I have 3, and then this is 1, 1, 1, 0, 0, 0 everywhere. And then I perform row operations below. Give this a try yourself to transform the left-hand side into the identity matrix. And suddenly, have a look. Here's a bar here for you. This here is the inverse. And this is the identity matrix. You totally didn't know that. Just kidding. Okay, so there you have it. I strongly recommend you guys to actually give this a try, as in go ahead and do A minus 1 times A. Do you get I3 back? Right? I mean, maths is not just a spectator sport where you just sit in a lecture and just listen to what the guy has to say. It's your job also to go ahead and verify some stuff for yourself to give yourself some much needed confidence. So there you have it. That's how to invert a matrix. Do we have time for a second example? Oh, this is an example of what happens if things go a bit astray. So here's another matrix that we want to get the inverse of. Some of you might have already noticed that this matrix is not invertible. Let's actually see what happens if you do the same process. So here's the augmented matrix. We do some row operations. I'm not going to show them to you. You guys, it's for you guys to do. And oh, look, this last row here is just a bunch of zeros. Something's a bit off. I don't think we can reach the identity matrix on the left-hand side anymore. And because of this, the matrix is not invertible. So as you can see, this method we have allows us to not only determine the matrix, the inverse of a matrix, but also determine whether a matrix is not invertible. Okay, we're at the quick quiz now. We're actually on time. We'll have to move a bit quicker though. So for all parts of the questions, assume that A is m times n and B is n times p. All right, Brian, I hope you're not asleep at the wheel. Get the poll up. Rank A is the number of non-zero columns in A.
We can get
Yes.
a poll. Let's do it. Okay. Okay, so question 1, true, false, polls running.
Yes. Think about this.
Just got back and now it's a quiz. I'm sorry, Larcy.
Don't worry about that. You'll be able to watch the VOD at the end of everything, and then you'll be able to pause the video and give your own guesses, although I won't make fun of whatever wrong answers you make. Okay, so unfortunately, I suppose, what was it? I suppose we don't have any votes. We have a false down there.
One false, yeah.
Yeah, we have one false. And luckily for that person, I hope it's not you, Penn Center. It is correct. So the idea is that I talked about this earlier. Rank A is the number of is the dimension of the columns, number of linearly independent columns in A. So it's not the number of non-zero columns. People can mishear things. I do it all the time. So it's of course nice that we have this quick quiz here to clarify things, just in case. All right, the zero matrix is the only m by n matrix with rank 0. Let's get that next question up.
It's posted on Twitch. You are welcome to add true or false if you would like.
I'm gonna peek at Discord as well, because I haven't done that in a while. Oh boy. Oh, we have 2 people in Discord. We have Driz in Discord saying false. Okay, feel free to give your explanation too. We have a true in Twitch, so interesting. One of you guys is going to be wrong. All right, that's been more than 30 seconds.
I think Drizz's false was for the
true.
first one, right?
Yeah. So the reason why it's true is because, think about it. We have a 0 matrix here. Everything is just big fat 0. Where is I of R? I of R is non-existent. Is there even an I of 0? Is that a thing? No, it's not. It can't be a thing because that's not an identity matrix. Never mind, but you get the idea. No matter how hard you try to fit in an identity matrix somewhere here to not get a 0 matrix or whatever matrix with rank 0, you just can't. So it's the only one with rank 0. All right, next one. Elementary column operations do not necessarily preserve rank. Here we go. Get that next question up.
All right, poll is live on Twitch for you guys. Joe says guessing works on Twitch. Fantastic.
Guessing does work. Running away is also a valid tactic. Although running away does usually entail that you won't learn anything. So maybe don't run away. Okay, so we have a false in Twitch, and we have, what do we have in Discord?
Driz
is still typing. Row operations preserve rank. Okay. I'm gonna wait a bit longer for Driz. Not true for column operations. Okay. So I'm not sure if you actually were here for the rest of this section, but this is false. And the reason is because don't necessarily preserve rank. This is false because let's say you have a matrix A here. Remember that we introduced a theorem earlier. The rank of a matrix of a matrix A multiplied by an invertible matrix. So let's say this is an invertible matrix here, is still the same as rank of A here. And G can be composed of elementary column operations, right? So because elementary column operations are invertible, and if you put them together, that's an invertible matrix, then they do preserve rank. So therefore, the opposite of this statement is true. It's false. There you have it. Okay. Oh, I think we'll do like one more of this and then see how it goes. Okay, so question 4. Inverse of a matrix can be computed using only elementary row operations.
All right, poll is live for everybody.
Joe, I am asking questions that I talked about in the lecture. We have one true in Discord. Sorry, in whoa, I have 2 Discords open. Oh my god. Oh, Driz says it's a trick question. True if the inverse exists. Okay, we got 2 truths. And yes, this was a trick question to catch you guys. This is false.
Ooh.
I'm going to show you something very interesting because you guys are going to learn from this experience. What happens if I multiply the right-hand side of this augmented matrix by A of -1? What happens? Look at this. This becomes A of A inverse, and this becomes I3 of A inverse. So we end up with I of R here, I of R here, and this is A of -1. There you have it. So A of 1, because it's invertible, can be written as a bunch of elementary column operations. Finitely many. So there you have it. You can use column operations, though it's just not as intuitive as using row operations. Yeah. But yeah, I hope this was pretty interesting to you guys. Got 'em indeed. We have a bunch of not like this is in chat. But yes, there we go. That's our section 2. I'm surprised at how close to being on time we are. Let's actually consider the theoretical aspects of solving a system of linear equations. We're getting there, guys. So first we need to actually figure out or like define what the hell is a system of linear equations. So here we go. It's a big fat definition. So let's say here's your coefficients. This is your unknown variables that you want to solve, and these are your right-hand side values in your system. Then there you have it. Here's your right-hand side values. Here's your coefficients here. And there's your unknowns like this. And well, since you have n unknowns, then you have kind of like n columns here. And since you have b different right-hand side values, then you have m equations like this, and your coefficient matrix should also account for this as well, since you have m rows and n columns. And therefore, I can just write the system as a of x equals b. So to see this a bit clearer, I'm going to write this at the side, a11, a12, 21, a22, like this. And then here's x1 all the way down to x of n. And then this is equal to, I think I might need the eraser for this one so you can see it a bit clearer. There it is. No, I don't want a marker. Markers are for whiteboards. We're on a PDF reader. Only Chads use PDF readers. Okay. And there you have it. That's how you can view it. X of the first row, the first equation, can be seen as this vector multiplied by this row, taking the dot product, and then the second row with the second row here, and it will correspond to B1, B2, etc. Okay, that's to make sure we're all on the same page. A solution S is a valuation of X satisfying the above equation. So if you find an S such that X equals S satisfies this equation, then you're all good. You solved the linear system. And the set of all solutions is called K, for lack of creativity. We'll call that the solution set. Keep this in mind. I'll re-jog your memory by saying set of solutions with K, okay? It's like hypnosis. All right, here's an example. All right, so here is a linear system. You can see some of the coefficients are missing, which means they're just zero. Here's your parameters. So A is your matrix of coefficients. B is your right-hand sides, pretty obvious stuff. X is your unknown coefficients. Notice how the first row doesn't have an x3. That's because it's being multiplied by this 0 here in A. Same idea with the 0 over here when it comes to the second row here, where there's no x3. All right, that's our linear system example. Let's actually talk about a special type of linear system where b equals 0, the 0 vector. So everything on the right-hand side is just 0. That is a homogeneous equation. Otherwise, it's non-homogeneous. If you're a non-English speaker, you're gonna stumble over this. Sorry, not sorry. I didn't make this up. Blame the people who first invented this theory, not me. Any homogeneous system that has at least one solution, any homogeneous system has at least one solution. And the one solution that will always exist no matter how hard you try otherwise is the 0 vector. Pretty obvious, right? Just think about it. A times the 0 vector. Damn, everything in this matrix A gets invalidated. Ha ha ha. All right. So here's a little thing to think about. Let's say you have your homogeneous systems and you have K, your set of solutions. Then K is basically the null space of L of A. So the linear transformation associated with A. Meaning the solution set K is a subspace of F of N, and the dimension of K is n minus rank of L of A. I mean, to see why this even happens in the first place, I didn't give you the proof, but I mean, just think about it. Since A equals L of A, basically, like this, then the set of solutions to L of A of X equals 0 is just a bloody null space by definition. So hopefully this allows you guys to basically rejog your memory on that and allows you to like link linear transformations to homogeneous equations too. Here's an example. This is a homogeneous system. I don't have to give you the unknown variable vector because that's that's pretty obvious to think about. But yeah, that's a homogeneous system. It's literally the same as the previous example, except B is now the zero vector. Okay, now, why do we think about homogeneous systems, the ones with B equals 0? Because there's a very strong relation to non-homogeneous variants of literally the same system. Which is why we have this definition here saying if you have a regular system, then you have its homogeneous counterpart. And basically, if you basically have a solution set for the homogeneous variant, which is called K of H here, then you can infer the solution set for the original system, AX equals B. And that's pretty much equal to, basically you get to choose any solution you like from the solution set K, and then you can just add any other solution from the homogeneous equivalent. So to see why this is the case, let's actually think about this for a bit. So remember, we're trying to say that this is what we're trying to prove here. It's inequality between two sets. So we need to show the subset from left to right, and then we need to show the superset variant. So this is left to right first. So let's say W is in K, and we have A of W is B, because W is a solution to the original system. Now, if I grab S, and then subtract it from W, like this, then I have AW minus AS by distributivity. This gives B minus B, which is 0. Remember, A of S is S is a solution from K, so therefore A times S is 0. Okay, so that means W minus S is a homogeneous variant solution. So if I go ahead and let K equals W minus S, or a more compact form, encapsulation, then by rearrangement I just have S plus K here. Like, just think about it. Remember, K is in K of H. By definition, W minus S, right? So if I add S to both sides, then I should have S plus K. K is in K of H here, and S is in the set including only S. Who would have known? The the element is contained in a set that only has itself. So there you have it. We've proved the left to right variant. Have I missed anyone? Okay, here we go. All right, to show the other direction, here we go. Let's say W is in S plus K of H. Then you can write W equals S plus K for some K in a homogeneous solution set. Then if you go ahead and left multiply by A, then you'll end up with B by distributivity, which pretty much means W is in K, and we're pretty much done here. Okay, that was some pretty full-on theoretical stuff. Let's actually see an example now. Okay, so let's say you have this linear system here. It's a boring system, not really, because it has one solution, and it's pretty obvious too. This is x1, this is x2, this is x3. So if I just plug 4 here, zero everything out, and that's a solution. Okay, hopefully no one will ask me any more questions on that. Oh, cluster, why is that a solution? Okay, moving on. So now let's actually go ahead and focus on the homogeneous system. So basically, just set that 4 to a 0. And I'll let you guys verify this for yourself. It has a solution set that looks like this. Basically, you have T of 1, T of 2 here, which are real numbers. These are the vectors in the solution space. They're like basis vectors pretty much. And now all you have to do is add the initial solution that you found from the non-homogeneous variant. And there you have it. That's your original solution set. Very nice. Once again, verify this for yourself. All right, so now we know how to solve a linear system based on a homogeneous variant. Let's actually think about how many solutions there are in a system. So let's say you have ax equals b be a system of linear equations, and basically the coefficient matrix here is invertible if and only if the system has one solution only, namely this one. Okay, why does that work? Well, the intuition behind it, I'll just say it real quick. So if A was invertible, basically what you can do is you can multiply both sides by A minus 1 here. This becomes x equals A minus 1b, like that. And A minus 1 is fixed. It has no variables in it. Same with B. Therefore, this is a constant vector, so to say, which means there is only one solution. That's pretty much the intuition behind it. To actually rigorously show why that's the case, let's actually go from left to right. So that means let's assume A is invertible. Okay? This is a solution because if you plug it in, which is kind of like multiplying both sides of your system by A inverse, but in this case, you'll end up with B as usual. It's pretty obvious. Now let's suppose for a contradiction, there's another solution. Okay, if there's another solution, what happens? Well, AS equals B, and by invertibility of A, there you have it. S is the same thing as X, which was our original solution. So we have a contradiction. There is no other solution. Let's go the other direction now. Let's say there's only one solution. So if you have K of H, your homogeneous variant for the system here, A of X equals 0, then you'll have K equals S plus K of H. But this only happens if K of H is the 0 vector. So consequently, the null space is 0, and therefore A is invertible. Okay, here's an example of invertibility up our doorstep. Basically, if you have A being your coefficient matrix here, take the inverse of both sides like this, and X will consequently be this solution here. You can also actually check that row reducing the augmented matrix will give no free variables, which also indicates that the solution above is unique. Give it a try. Remember, I'm going to say it again, multiplying an augmented matrix by an invertible matrix on the left-hand side, for example, we'll just kind of do this thing here. This becomes I here, and that's your solution. Okay. Now, there's another term I want to bring out here called consistency, and the idea is it's consistent if it has at least one solution. That's what a linear system will be. Consistent if it has at least one solution. Otherwise, it's inconsistent, just like my sleep schedule. Now, there's a theorem here which says if a system of linear equations is consistent if and only if its rank is the same as the rank of its augmented kind. Now, why is that? Well, this is pretty much equivalent to proving that B is in the rank of L of A. The intuition behind this is that the rank of a matrix, I'm reminding you this, the rank of a matrix is the dimension of the span of its columns. So A of I, this is I equals 1 up to N. So The rank of a matrix is the dimension of its span of the columns. So if you can show B is in the range, then this consequently means that B is a redundant vector in the span of A, which consequently means if you just remove this B here, since it doesn't contribute to the dimension, it doesn't add to it, then now you have the rank being the same. Give this a try. Prove this rigorously. This is exercise 9. Of course, after the lecture. Now that we have that intuition out of the way, we also know that the range is the span of each column. I said this just now. Therefore, A of x equals B has a solution if and only if B is in the span. Okay, very nice. And this happens if and only if, of course, A1 to A of n is the same as the span, including B. And this also happens if the dimensions have to be the same, which therefore reduces to rank of A is equal to rank of A and B in a augmented matrix. Okay, let's actually see an example of this. So here's a non-standard linear transformation. It's not written as a matrix, not yet anyway. And I basically want to know the rank of it. And I want to check if it's the same as the rank of the augmented matrix. Now, I want to see if 3, 3, 2 is in the range of T. So this is literally the same as solving for S in this little thing here. This little equation here. It doesn't look like a linear system, not yet. But if you transform T into, excuse me, that was a burp. If you transform T into a matrix like this, then you can easily see that rank A is 2, like this. But the rank of the augmented matrix is 3, meaning that B is not in the span of this of the columns of this matrix. Can you see why if B is not in the span of the columns of the matrix, then there is no solution? It's like how do I say this? So since you couldn't get a solution for B, then that means B is not in the span. And therefore, if you go ahead and concatenate B with the rest of the matrix, the rank of the matrix will actually increase. The dimension of the matrix will increase by 1. And therefore, this is what causes the rank of A to not be the same as the rank of the augmented matrix. And that's why B is not in the range of R of T. Pretty interesting stuff, isn't it? I'll just quickly look at Twitch chat to make sure anyone still here. Okay, good stuff. All right, so to summarize, what have we done? Because we kind of did quite a bit in this little section alone. We formulated a system of linear equations problem into a linear algebra one involving vectors and matrices. It's a lot easier to deal with because we spent the last 6 lectures, and now here's the 7th, in basically getting everyone up to speed with any theoretical aspects of linear algebra. We can apply those theoretical aspects when you solve a linear system. That's why being able to transform, reframe a system of linear equations into a linear algebra problem is so important. So that pretty much explains pretty much the entirety of this slide. And from here, we're just in time for our quick quiz. Brian, get ready to go. First question, any homogeneous system of equations has at least one solution. Vote now.
All right, poll
Off
is
you
up.
go.
What do we think? Any system? Okay, so any homogeneous one solution. Okay, I think I know the answer to that one. Also, I really liked your proof of the It was that one where I said, like, am I being dense? Because I couldn't follow the proof, and I think it got cleaned up super nicely, and I was really able to follow your explanation there. So thank you very much for that.
No worries.
Peak and flow.
Well, that's
No,
a
these
really
are
good question by Peak and Flow.
Yeah, so these are separate from what Zach and I are running starting on January the 20th. So January 20th, that's going to be kind of a brand new problem-solving focused course. We're starting that from scratch. So you do not need to catch up on the other 6, although if you'd like to watch them, we're not going to stop you.
Okay. Very nice. So that's the end of the poll. That is true. Remember, a homogeneous system looks like this. It has a 0 on the other side. So the easiest solution you can think of for any homogeneous system is just x equals 0. That's why it's true. Just invalidate that bloody matrix and you're done. Okay, next one. If the coefficient matrix, that's A by the way, of a homogeneous system is invertible, then the system has no non-zero solutions. Let's have a think about this one for a moment.
Yeah, Drizzt, the University of Penn Center, maybe. We're trying to get our
Oh, true.
trying to get our nonprofit up here in Canada. It's a slow moving process.
Okay, here we go. All right, so that's more than 30 seconds. That is true. And the reason is due to one of the theorems we saw earlier on non-homogeneous systems here. Let's say A is invertible, then your solution is A minus 1 of B here. But what if B was 0? Then this is just A minus 1 of 0, which is 0. So there you have it. We have absolutely no non-zero solutions whatsoever. All right. The solution set of any system with n unknowns is a subspace of f of n. I think this is our last question. I could be wrong. By the way, guys, I hope you can see that there are polls. It's for engagement, yeah? Don't,
I wonder how many of our 18 viewers have accidentally fallen asleep. That's what I'm wondering.
I mean, the time zone is a bit weird for you guys, isn't it?
Don't see any polls? They're up at the top. You have to go to the top of the Twitch chat. And then you can select T or F.
Bros. Yeah.
Twitch puts them in very weird spots. I apologize.
Bros. Okay, so we have 1 vote for false. Unfortunately, that is true. Now, why is that? Let's have a look at so it has n unknowns, right? Which means there are n variables, x1 all the way to x of n, like this. Here's a coefficient matrix, and here is B here. All right, now, if you go ahead and suppose that you have U and V as solutions to A of x equals B here. If you go ahead and say U and V are solutions, then what happens? Then we have A of U plus V here. That's A of U plus A of V here. Remember, I'm trying to show that this is a subspace of f of n. I'm talking about the solution set. U and V are both solutions. So we have B plus B, which is actually 2B, which is not a solution, not necessarily. So this is actually false, my bad. When would this actually be true, though? When would it be true? Would anyone like to quickly answer in chat?
I think Drizzt might have a solution to that one.
Has to be homogeneous. Very well done, Drizzt. Oops. Very well done. So if B was equal to 0, then suddenly, yes, U plus V is a solution and is therefore in the solution set. and same with a scalar multiple of u. Very well done. So it's a good thing we kind of went over this for a while. So very well done. Okay, now last section, computational aspects. So now we're actually going to talk about the most efficient way to actually solve a linear system. Remember, we spent the last few sections formulating and formulating and formulating. This is the most important section, the biggest takeaway when you're applying this theory to most applications. All right, so let's actually talk about what happens when you have the same solution set in two systems. They're equivalent, that's what we call them. Okay, now, what's the relation with invertible matrices? Well, let's say you have C, which is invertible, and you have a linear system. Then if you multiply both sides by an invertible matrix, then you will get the same solution set as the original system. And why is that? Well, I'm going to say it again. C can be composed of elementary row operations. Yes, please don't ever forget this, particularly if you're going to continue studying linear algebra. So because we're doing a bunch of row operations or column operations, by the way, then not only does the rank not change, but the solution space, if you do it right, also shouldn't change. Okay. Proof is pretty simple. We're trying to show that, the two solution sets are the same, K and K prime. So because this is a set equality, we need to show the two subset relations. So if W is in K, then you have AW equals B, since it's a solution, pretty obvious. Left multiplying by C means you'll get W in K prime. And guess how the other direction is going to be done? I think we're going to have an inverse in there somewhere. Oh yes, what a surprise. There's the inverse matrix to essentially get rid of the C and show that W is also in K. All right. Now let's talk about what happens when you have equivalent systems and their relation to augmented matrices. So let's say you have your system, you have system number 1 and system number 2 and their augmented matrices. Then the system is equivalent. How about that? Proof is pretty simple. It's due to the fact that when you have a matrix that is split into chunks, then multiplying on the left or right by an invertible matrix like this, or otherwise, means you multiply like the separate chunks on the left-hand side with the same matrix. There you go. You can pretty much just apply the same kind of steps you did in the previous theorem. Now, here comes a really, really important one. This is going to be quintessential or just essential in solving linear systems using row and column operations, perhaps. Here is row echelon form. All rows with only 0 entries are at the bottom. So let's have a draw about this. So you only have zeros at the bottom. If you have a non-zero row up here, this is non-zero, and you have zeros up here all the way, this is not in row echelon form. Every single row that has zeros in it must be squashed at the bottom. That's the first rule. The leftmost 0 entry of every non-zero row, oh god, which we call a pivot, is on the right of the pivot of every row above it. So what does it mean by this? We have a bunch of examples just below here. So as you can see, here is condition number 1. So here's condition number 1. That's a 0 row. It's forced at the bottom. The stars are arbitrary elements. They can be any number you like. The leftmost non-zero entry of every non-zero row. Okay, This is the leftmost, this is the leftmost non-zero element of this row here. It's on the right of the pivot of every row above it. So, okay, it's on the right of this pivot and it's on the right of this pivot. Thumbs up, good. How about this one? This is a pivot column because it's the leftmost non-zero entry of this non-zero row. It's a pivot and it's on the right of every other pivot that is above it, and so on. And by the way, I don't know if you've noticed this yet, but every upper triangular matrix is an REF. Have a think about that one for a bit, or not. So it's not just REF that we have to deal with. Like this is like an intermediate version of what we call the reduced row echelon form. And basically, it has to be an REF and every pivot is 1. So that means you see these elements here that are pivots? No, they must be 1. They must be 1. They cannot be anything else. Full stop. Each pivot column has zeros in every other entry. So that means if you have a 1 here, then everything above it is 0, for example. For example, you'll get to see a few examples in a moment. Here they are. See, here's a pivot column because there's a 1 here. Every other pivot's to its left, meaning it's an REF, and everything else is 0. And this is not a pivot column because there is no non-zero entry that has to be a 1, which means everything above it can be whatever you want it to be, and etc. And surprise, surprise, the identity matrix is in reduced row echelon form. There you have it. Make sure to ask any questions in chat if you're really stuck. Okay, now I don't know if you guys might have noticed this already, but given that this kind of does look like an augmented matrix where you have B and this is A here, RREF, reduced row echelon form, is the ideal form for solving linear systems of linear equations, and you'll see why in a moment. It's not just because it's so minimalistic. Let's actually walk through the solution finding process for one of these augmented matrices like this, okay? First, we transform it into row echelon form. So first, I want to get a 1 in the top left corner. So I just switch row 3 and row 1. Okay, then I go ahead and subtract row 1 from row 2 and row 3 from 3 times row 1, which gets us this matrix here. So you can kind of see how we slowly kind of turn this into a pivot column like this, and because this is now a pivot column, everything below it is 0 and we have a 1 here. We're going to work on the next column now. Next slide, please. Hello. There we go. So I take the negative of the second row. So this 1 here looks like it's a good pivot here because all I need to do now is transform whatever's below it into a 0 now. So I just have to do R3 plus or R2, which zeroes out the bottom part here. Okay, so now we have another pivot column with the 1 there for convenience. And lastly, it doesn't seem like we can get a pivot column here because the leftmost, no, sorry, not leftmost, but there's just zeros everywhere. So I think the next pivot column has to be here. So we divide by, okay, sure, it's an REF because, you know, this is a non-zero element, right? So we could theoretically go ahead and plug in our variables like x1 plus x2, 2x2, sorry, plus x3 minus x4 equals 2, and so on. But the thing is, there's still quite a lot of variables as you can possibly deduce. So what happens if we transform it further into REF? So I first divide by a factor of negative a third. Okay, beautiful. Then what I'm going to do is I'm going to get rid of this 2 here. Okay. Next slide. Incorporate machine. Okay. Now I'm going to perform row 1 minus 2r2, which gets rid of the 2 here. And then I'm also going to perform these 2 operations. You can try it yourself. That will basically turn these elements here into 0, thereby forming our pivot columns here. Beautiful. So if we actually go ahead and transform this back into a linear system, it looks a lot simpler, a lot nicer to work with. All you have to do is bring x3 to the other side here. x2 and x4, you know they have to be 2 and 3 respectively, and x3 is 3. Beautiful. There we go. And we can also write the solution space as a little linear combination over here. So x1 is 1, of course, from the one up here. x2 is 2, has to be. x4 is 3, has to be as well. x3 is whatever you set t to. Then you subtract 1 here to get 1 minus x3. Now, the process we used earlier to transform the augmented matrix into reduced row echelon form is called Gaussian elimination, or is it Gaussian? Which is the right pronunciation? I don't know. You'll have to decide on that yourself. And the theory is that Gaussian elimination transforms any matrix into reduced row echelon form. And imagine, you can just imagine how long-winded this proof is going to be. No, I'm not doing it. You're gonna read the book. We've only got 15 minutes left. So let's actually do another demonstration with a general solution, because I think it'll be nice if we see another example of this. So if we have an augmented matrix that looks like this, and we do Gaussian elimination on it, this is in RREF. So you have a look. These are our pivot columns here. Everything else is kind of borked. And this gives the linear system as shown below. Please verify that you can get to this row echelon form using row operations. Okay, by rearrangement, you can determine that x3 and x5 are free, and there's your general solution. Please tell me if I'm going too fast as usual. Okay, and let's talk about rank as well, because, you know, this is kind of where we tie everything together. Let's suppose the rank of A is the same as the rank of A with B put next to it with in an augmented matrix form. So remember that because the rank of A and the rank of the augmented matrix is the same, then that means the system has solutions. That was a theorem we covered like 10 or 20 minutes ago. Furthermore, let's suppose A with B in it is in row echelon form. Then what happens? The rank of A is R. Okay, I suppose you could do that. And if the general solution looks as follows, like this, you have S0 is some sort of solution in a non-homogeneous system, and U1 all the way to UN minus R is the basis of K of H. Then S of 0 is in K, basically. So to show 1, you already know A and B is in REF, meaning all R non-zero rows should be linearly independent. And I do not know what happened here. This is a typo. That's an A. Please bear with me, guys. Imagine trying to do this yourself, writing all these lecture slides. It's a bloody pain. But yes, the R non-zero rows should be linearly independent, because if you think about it, in RREF, you have your pivot columns that look like this. Everything else under it is 0, right? So there's absolutely no way you can write this row as a linear combination of the others, right? All the pivot columns, the leftmost elements in each row, they're just not going to do anything to make this a 1, for example. Okay, number 2. Okay, if we set all t of I equals 0, so that means this goes, everything else goes. You're just left with s of 0. It's in k, obviously. But also, we can write k as this solution, remember? As you can also write k as this solution plus any other solution from k of h. So by rearrangement, I'm going to move this set s0 to the other side, which, means you're subtracting s of 0. K I can represent as this set here, but this just means that s of 0 will cancel out. And this is literally, the resulting set is literally the span of each of these vectors here. And to show that it's a basis, you simply realize that dim of k of h is n minus r. And there are also n minus r vectors in this set here. So therefore, if you have the right number of linearly independent vectors, which is the dimension, by the way, then you pretty much have a basis. All right. And here's another way to interpret the row-reduced echelon form. Basically, if you have B as REF of A, then B has R non-zero rows, and for each non-zero row, there's a column. There's an associated column of BJI such that it's the it literally matches the standard basis with 1 in that entry. We should also notice that the columns that are corresponding to these BJI that are in A are also linearly independent. And lastly, this is pretty loaded, by the way, but should be fine. If for each k, the column k of B is can be written as this linear combination here, then the column k of A should be written as this linear combination right here. You'll see what I mean in a moment. These will make sense when I actually go through the proofs of them, and they shouldn't be too hard. Basically, since you managed to get from B through a series of row/column operations from A, then the rank is going to definitely be the same, okay? And R is the number of linearly independent rows. Since B is in a row-reduced echelon form, there should be R non-zero rows. It's pretty obvious by the definition of rank. Okay, now, for this one here, since B is in row-reduced echelon form, then it's made of pivot columns. So, for example, you might have a matrix that will look like this. Sorry, those should be zeros here. So let's say it's in row-reduced echelon form. It's made of these pivot columns here. In theory, that's what should happen by definition. And they are basically standard basis vectors, right? I mean, just look at this. This is in the standard basis of R3, which is very nice. So therefore, this is E of 1, E of 2, E of 3. And the rank of this matrix here is 3 as well. So it goes from 1 to R in this case, which is 3. Now for each 1 all the way up to R, this is going to be a bit confusing, but this should clear it up. I'm going to let J of I be the column index from left to right such that the corresponding column I reference is the standard basis vector. So in this case, B of 1 is E of 1, B of 2 is equal to E of 2, and B of 3 is equal to E of 3, like this. Very nice. And in this case, I would set J of 1 here equal to 1, 2 to be 2, and then J of 3 to be, so how many columns are here? 1, 2, 3, 4, 5. So this is B of 5. See that? Hopefully that should clear things up. So here I'm directly referencing the columns that are pivot columns and therefore, what was it? Standard basis vectors. So that's why there is a column bi of j such that bi of j equals e of I for each I up to r. Okay, can I please go to the next slide? Okay, there it is. The columns of A numbered ji to jr are linearly independent. So to make this clear, the pivot columns of B corresponding to A. The pivot columns of B that correspond to A are linearly independent. And to show this, like this seems far-fetched, but let's have a look at this. Let's say they're not linearly independent, right? Let's say they're linearly dependent. Then there should be constants such that this should be equal to 0, right? That's the definition of linear independence. Now, remember that there's an invertible M such that you can get from A to B. And remember, B is in row reduced echelon form, and M is basically our amalgamation of all our elementary row operations. Okay, perfect. So how about we multiply both sides of our linear combination with M? Then obviously we should end up with BJI here, like this, right? And since each BJI is the standard basis vectors, we know they're going to be linearly independent. So this is obviously independent, which therefore implies this is independent, and therefore this implies independent as well. And therefore, further up, you know, the AJ1, CK, etc. is also linearly independent because it uses the same constants here, see? Each CK must be 0. So therefore, this contradicts our original assumption of dependence, and therefore each corresponding pivot column is linearly independent. Okay, 4 is for you guys. Basically, you can get there by reversing the process of 3 using m-1. Give it a try in your own time. Now, the next thing I want to bring to your attention is that REF of a matrix is unique. That's an exercise. Of course, this will be presented in the exercises section. Give it a try. Ask questions too. Now, here's an example so we kind of don't lose ourselves too much in theory. So here's our matrix. Reduced row echelon form looks like this. There are 3 non-zero rows and pivot columns. See? Non-zero, non-zero, non-zero. So 3 pivot columns, 3 non-zero rows, meaning the rank is 3. Beautiful. Okay. The pivot columns, as I explained earlier, are linearly independent because they are standard basis vectors, right? So A1, A3, and A5 from all the way back here, see? These 3 vectors, here, these 3 columns are going to be linearly independent. Go ahead and verify this. And lastly, there's another thing I want to bring to your attention. It's about these columns that are not pivot columns. Notice how I can write this column here, B2, as 2 times the first column. right? It's linearly dependent on the first column. And also, I can write the fourth column as 4 times the first column and minus 1 of the third column. So therefore, back in the first matrix, back at A, you can do the same thing with the same multiplication constants. Verify this. Right, we're running out of time, so I'm going to move a bit faster now. Here's an example where we basically show you how you can extend a bunch of vectors, linearly independent vectors, to a basis. So basically, I have a collection S of vectors which are linearly independent, and they are a subset of U, which means they're all solutions. All of these are solutions to the system shown above. Please verify this in your own time. What happens next? To extend S to a basis of U, what I first want to do is get a basis, and then we're basically going to cherry pick vectors from this basis, and then plug them into a S here to extend it to a basis here. Okay, so this can be obtained by using the linear system. As usual, I rearrange to basically figure out what x1 should be. It's bound, the rest are free. And we basically have this general solution here to the system. And these here can kind of be seen as basis vectors. They're obviously linearly independent, and they span U as well. So now we want to figure out which vectors here can we choose to include in S, right? And how do we do this? Next slide. There it is. So we can't just grab all the vectors and just join them into S, right? Because it's going to be linearly dependent. The dimension of the span of this here, which is a basis, is 4. So that means S should only have 4 vectors in it, not 7. That's pretty bad. So what's the solution? Make an augmented matrix where you have your vectors in S and your vectors in B here. And then you reduce to row echelon form. What's the consequence? You have your 3 vectors here, which are from S, as pivot columns. And oh, look at this. You have a pivot column over here, which corresponds to this vector. So intuitively, if I were to grab S and then just simply add this vector in here, you now have a basis. Thumbs up. And it makes sense as well because the rest of the vectors, as you can see, are linearly dependent. This vector here, this column, can be written as this column plus this column, and therefore in the original matrix here, you can add these 2 columns together and ta-da, you have linear dependence there. Feel free to have a read over this in your own time. Okay, now, we're actually out of time, but Penn Center, if you'd like, are you okay with doing the quick quiz?
Absolutely.
Or should we not go any further over time?
We're doing the quick quiz, whether you want to or not.
Okay, we're doing it, because it shouldn't be too bad. Okay. If you can get one augmented matrix from another by a finite sequence of elementary column operations, then the solution sets are equivalent. Is that true or false? This one's we're starting off with a pretty difficult one, I think.
We have 1 false on Twitch so far.
Okay, how about Discord? Do you have anyone on Discord? No.
No, we're pretty
no
quiet
answers
on
yet on
Discord.
Discord.
So I think false is going to be our winner on Twitch.
Okay, here's an interesting thing to realize. It's actually true. Why is that? You can obtain via a finite sequence of elementary column operations. Why can you do that? Isn't that weird? Well, if you think about it, what if we go ahead and took the transpose? Actually, can you even get the A prime, B prime using column operations? I think there'll be dimension mismatches. There'll be dimension mismatches, right? If you try and do column operations, then you'll kind of get yourself in a pickle here. Or will you? No, you won't. You can do column operations. But then X is in the way, so you can't really do it. Okay, so I think technically this is actually false. That's my bad. Because of the technicalities of when you multiply on the right-hand side using column operations. However, you can go ahead and take the transpose of both sides, X transpose, A transpose. Then from here, you can do your column operations. Then you can reverse the transpose of whatever it was, and then they become row operations again. Okay, so that's an interesting way to look at it.
Right,
Okay,
okay, yeah.
if A is a square matrix, sorry?
I was just saying, yeah, that makes sense. And the size mismatches was a good noticing there.
Yeah. So once again, please ignore the true here. This is a F here. F to pay respects. So if A is a square matrix and the rank is n, then the row reduced echelon form of A is the identity matrix. Is that true or false?
All right, we got 2 trues. True is coming out strong.
Finally, we got more. Let's go. Okay, so in that case, whoops, if you actually go ahead and go to next slide here, it is true. And it's pretty simple to realize why. When you have rank of A as n, then you must have n non-zero rows. So all of the n rows here must be non-zero. And we must have n pivot columns. So therefore, you are going to have all of these n elements on the diagonal. See, look at this. Which is therefore the identity matrix. Pretty simple stuff. Very well done.
Yeah, and Driz had a good comment.
Any matrix.
Driz had a good comment too, that
this.
the product of the elementary matrices is going to be our inverse too, right?
Mm-hmm. Exactly. Very well done. So here's question 3. Has vote on your phones or whatever. At the top of the chat, in case your screen is tiny. If you don't have a touch screen, then you're poor. Wait, then that means I'm poor, because I'm on a laptop and I don't have a touch screen. Oh no! Okay, nevertheless, we got 2 votes for true, and okay, let's be honest here. It's been rehashed and reiterated so many times during this chapter that this is pretty much free. All right, if the augmented matrix is an REF, then it's consistent. Let's see what we get on this one.
That's 4, right? Give me a second here. Okay, poll started.
Here's a fun fact, guys. You can always be correct if you wait for the answer and then input the answer into the poll.
So I got through all my math classes in undergrad.
I don't recommend it. This isn't brilliant.org.
We got 2 falses in Twitch and 1 true so far.
Okay, here we go. The answer is false. And there's a very good reason why this is the case. If there's a case where I can make a row reduced echelon form of a non-homogeneous equation where I have 1 in the bottom here and everything else here is just 0, right? Everything else can be whatever it wants to be, because what happens down the bottom here? There are no there are no coefficients being multiplied by any unknown variables. So literally the left-hand side is 0 and the right-hand side is 1. Oh no. That does not look like a feature of a consistent linear system. So that's why we give it false here. There you go. I don't think we have any more than this. No, we don't. And unfortunately, we are out of time. So for the application here, this is basically a Markov chain. If you're familiar with the theory, then you don't have to read it. However, if you are not, then I think you'll find this definitely interesting to read over. I think it's a better example, like a better application, than the one which which Friedberg included in his book, because I personally couldn't understand it. It was an economic example, like an economics example, and it was a bit difficult to make sense of, because I don't think modern economics works in, like current economics works the way it does as presented by Friedberg. On the other hand, when it comes to Markov chains, they kind of do make a bit more sense to me. Who knows, maybe you'll find their version better. But yeah, give this a read in your own time. And yeah, I think that's everything I've really got to say. I'm really surprised. I'm really impressed by for the matter, that I did manage to get all the way to the end of all the theory and quizzes and everything in the time that I did. It's amazing.
I knew you had it in you. I knew that you were going to get the job done. Driz on Twitch
I mean,
is
just
saying
think about
thank
it, guys.
you.
Yes,
There's a
no
lot in
worries,
there,
Drizzy.
right? There's a lot. Driz and I were talking. It's a pretty dense chapter, and the fact you're able to summarize it so succinctly, I really appreciate that.
But let's be honest here, I couldn't have done it without your help, because if I didn't like ask for feedback, then we'd be over time, given I would have included some other questions in there that would have been a bit redundant, or like some proofs that would be way too long. We'd be wasting so much time on that. It's insane. But yeah, if you think about it, you know, as well, there's 302 pages in this presentation. If you were to give this a single glance, you would go, there's no way you can cover 302 pages in a single 2-hour lecture. No way. I mean, even up to where we left off here, this is 285. It doesn't seem possible, but you know, I did my best. Thanks, guys, for tuning in. Really, it's really I really appreciate it, honestly.
We obviously I from the bottom of my heart, I appreciate you joining us for a couple of fantastic presentations. I know that chat really appreciated all your dad jokes. You know, we're throwing LOLs in the chat every time one of your dad jokes pops up. It was a bit weird tonight, right? Because it was definitely more, I think, Twitch focused. We got up to about 20 viewers there at our peak, and we're kind of hovering around 15 right now. Getting a couple of good lectures. Thank yous again from Driz and Joe. So thanks again, Cluster. And are you able to get the updated slides? There's no huge rush, but whenever you get a chance, feel free to send them my way, and we can get them posted into a simple server for everyone to review.
Oh, I can literally just do it now. I'll just save this main.pdf, and that's the annotated slides. They're gonna go straight into the Discord server,
That's
and you will
amazing.
be able to make memes about it.
I cannot wait to make memes. It's like all I do all the time.
Yeah, it's public domain, isn't it? Or, you know, Creative Commons, whatever it is. Where's the serial bit? Here it is. Oh no, I can't post in there. It's only for you, angry face. So I guess it's time to put it in discussion.
Yeah, discussion works. You can post it into the
Okay.
like our little presenters chat, whatever's easiest.
Yes. So there it is. There's our annotated slides. It's unhelpfully called main.pdf. I have to compile the slides again to get the unannotated versions. But yes, there you have it. Well, I could be British, but if I kind of, you know, feel a bit more casual over here, then do I sound British still? Yeah? You know, do I still sound British?
There's a couple words I think that give it away, but it's so, why is everyone popping into chat asking if you're British tonight? It's so funny.
Look, the thing is, if I'm trying to be really like careful, I tend to put on like a UK accent. But when it's all casual, then I can speak like this all day, and I can talk like Russell, the voice bot. Yeah.
Oh my gosh, you do sound like Russell when you do that. That's amazing.
How does Russell say? You know, I've been called out for being a robot, yeah, for sounding like an AI, and all I do is say yes, and I double down on the act because it's fun. Okay, you can do some very funny intonations on certain things, and it will make people feel really awkward.
Problem solved.
All right, Drew's still here. Sweet. We're gonna
QED.
give some of you boys some QED points for coming and hanging out tonight. Let's Joel. Ma, there you go.
Hardly even a practice test.
You're at 31? Holy cow, Joe. That's crazy. All right, thanks again, Cluster. Let's
Yes,
see.
no worries, and thank you to Penn Center, and see you guys hopefully in the next time I present or in another lecture. Yes, we're all excited for that.
Great. That sounds great. We're going to get a raid started over on Twitch. We're going to go see what physics and depression is up to. So
Oh
have
no, not depression.
physics and excitement. We don't get a chance to raid physics that often, so we're going to do that right now.
Whoa.
Have a fantastic night, everyone, and we will talk with you soon. Bye now.
Bye.
Set a laughter. But don't get distracted by memes. Focus on
And
the
we are
equations of
offline.
life, where my genius reigns
Amazing.
supreme.